So there is one simple motivation that I will try to keep in mind when doing double integrals. Think about a planar region, a plate, and think about that plate having different density at different points. So the density depends on the point, and of course we assume there is a coordinate system in that plane. And then the question is to compute the total mass of that plate. So if the density is given, find the mass of that plate. Because of course, if the density is constant, then the mass is simply the area multiplied by that density. And assume the density is weight per area, not per volume. And so we are in flat situation. But if the density changes, the answer is definitely not simply some number for the density times the area. And then the idea is that we can use some sort of integration. And the idea is technically about taking that area and, well, let me start with a very simple region being a rectangle. So you have a rectangle and you have a function on that rectangle. And of course that happens in the assumption of chosen coordinate system. Then what you do is you can cut that plate into small pieces. And then for a small piece, you argue that, well, for that small piece, you can probably find the mass of the piece approximately. And the way you do it is by finding the density at that point, somewhere in that piece, and multiplying that density, that value, by the area of the piece. So why are you eligible to do this approximation? Well, because you assume that the density doesn't change quickly in a small piece. So the density is approximately the same in the whole piece. And if the density is the same, then the mass is density times the area. So you cut in the effort of bringing that formula that mass is density times the area. And that formula doesn't apply globally, but it applies locally, approximately. And so that serves like linearization of the problem. The analog of what we did previously, like Hooke's law and all kind of linearizations in case of one variable. So we replace the global problem by local, and as you localize, you identify a law like this, and then you use that law to say that the total mass is the sum of masses of all those pieces and using index k, the summation will run over all k's, and then for each of those pieces mk is approximately density at that piece, rho k, multiplied by the area of the piece. And then, at this point, when you look at the sum, then there is standard form of that sum that is denoted by an integral after you pass to the limit. So, because the next argument is that after you subdivided, you approximated each mass, you added all those masses, that's going to be only approximation for the actual mass. And then you keep subdividing further, computing all the masses, adding up, and getting better approximation. And then limit of those approximations is the actual mass. So let's work out the notations without referring too much to the motivating example.